So today we're going to talk about balancing redox reactions in basic solution. It's very similar to the process for balancing reactions in acidic solution. The difference is that you're going to have not only some water and hydrogen ions to work with, but you're also going to end up with hydroxide ions whenever we get done. So let's look at our first example here. Again, I could go through the rules, but they wouldn't make sense until I actually showed them in action. So the first thing we want to do is to write these in acidic solution, but if you notice they're already in, write them as net ionic equations, but they're already in net ionic equations, and the easiest way to tell that is to look to see if you see any charges. If you see charges up there, you can be pretty sure that it's already in net ionic form, which just takes care of one of the steps for you. So if you look at what we've got here then, silver is 0 for an oxidation number. Oxygen is 0 because it's in its elemental form. Water, as usual, is +1 and -2 for the hydrogen and oxygen respectively. So now let's look at cyanide. We've got this adding up to a -1 because it's a polyatomic ion. The nitrogen is a -3. That leaves the carbon with a +4 charge. So we've got a -3 and a +4 for our carbon and nitrogen. And then on the other side, since cyanide is a negative charge overall, we should know by now that silver as an ion only has one possible form, and that's a +1. And since this is cyanide again, cyanide is cyanide is cyanide. Its charge is not going to change. Its oxidation numbers are not going to change. So it's still going to be +4 and -3 for our carbon and nitrogen. So let's look at what's happening here as far as our um, oxidation and reduction are concerned. If you'll notice, silver is going from 0 to +1 stage, so that is our oxidation. And oxygen is going from 0 down to a -2, so there's our reduction. So let's write those. Now it's already in net ionic form, remember, so we cannot further ionize or break down anything that's in net ionic form. So our oxidation is going to be Ag going to AgCN2 with a negative. And the first thing we want to do with that is to get it balanced by mass. The silver's okay, but of course the cyanides are not, so we're going to need to add 2 cyanides over here to get that balanced. And since we're going from 0 to +1, as we said over here, that means we're going to need an electron over here to get that balanced. Our oxygen then, O2, we cannot further break down the H2O. It's got to stay H2O. So the first thing we've got to do is get our oxygens balanced by mass. And so we're going to need a 2 in front of that H2O to get 2 oxygens on both sides. Now remember, we're going from a 0 for our oxygen's oxidation number. And since oxygen on the right-hand side is a -2, but there are 2 of them, that's a total -4. So we've got a 4 electron change going on here, which means that we're going to need to add 4 electrons on this side in order to get those electrons balanced. So we now have our electrons balanced, and we balanced by mass for the element that's changing charge. But let's see now what we have to do, what we have left. Notice in that bottom reaction we still have hydrogen ions. Now, we're going to do the same thing we did with acidic, but we're going to have to go a step further, because if we put our 4 hydrogen ions on this side, that's all fine and good if that's an acidic solution, but this is not an acidic solution. This is a basic solution. We cannot have hydrogen ions in our basic solution. So in order to get our hydrogen ions canceled out, if you will, what we're going to do, since this is basic solution, is we're going to add 4 hydroxides to this side Think about what that does. If we add 4 hydroxides to this side, we've got hydrogens and hydroxides. Keep in mind that that's exactly what we need in order to make water. So what we actually did there was cancel out our hydrogens and make water. Now, we can't just add 4 hydroxides to one side just because we feel like it, because if we put 4 hydroxides on that side, on the left side, we've got to add 4 hydroxides on the right-hand side as well. So that's our extra step. Once you've balanced with the oxygens with water, once you've balanced the hydrogens with hydrogen ions, then our final step has got to be to add the same number of hydroxide ions to both sides so that we can cancel our hydrogen ions, if you will, and make water out of them. So what does that leave? It leaves 4 waters on the left-hand side and 2 on the right-hand side. So what can we do there? We're going to cancel out the waters on this side, and we're going to leave 2 waters behind on this side. So now that we've done that, we can go through and we can balance for the electrons. We've balanced by mass, and now let's balance for overall electrons. So we're going to need to, it looks like, multiply this top reaction by 4 in order to get 4 electrons in both reactions, both half reactions. So this makes that a 4, this a 4, this a 4, and this an 8. And we've used that up. So let's see now what our overall reaction is going to be. So what we have left over are 8 CN minuses and 4 AGs. And then on the bottom we have 2, it's not a very good 2, but 2 H2Os and O2. Remember our electrons, our overall electron changes are canceling out. Then on the other side, we have 4 silver cyanide complexes. We'll learn more about those later. And 4 hydroxides. So overall charge looks like we have 8 negatives on the left-hand side and 4 plus 4, 8 negatives on the right-hand side. So it looks like everything balances out. So this is our final reaction for that one. Okay, then let's look at our final example. I tried to throw some that were a little different at you and had some weird things going on. I can't always give you problems that have just situations you've seen before, because the AP test is absolutely not going to give you just things you've seen before. There's always going to be something on the AP test you've never seen before, and you have to be able to adapt to that and think a little outside the box. So let's look at the next one. Looks like it's already in net ionic form because of that 2 negative. So looks like we have chromium at 0 here. And since this has to add up to a -2 since it's a polyatomic ion, our oxygen's a -2. That gives us a -8 for our total oxygen charge. Looks like chromium has to be a +6. Over on the other side, looks like we have a negative for our hydroxide. That gives us 3 negatives overall for our hydroxide, which gives us a +3 for chromium. And of course, we know that our oxygen and hydrogen then individually are going to be -2 and +1. So those are our charges. Now this one's a little bit of a glitch. Let's see what's going on here. Looks like oxygen's not changing. There actually aren't any hydrogens on the left-hand side. We're definitely going to have to fix that when we do our overall reaction. So this is something a little strange that happens. It looks like we've got chromiums involved in everything, because look at what happens here. We've got chromium 0, and it's going to go up to +3. But looking at our other species over there on the left, we've got chromium right here as a +6, and it's going down to a +3. Looks like we've got both oxidation reduction occurring with our chromiums and meeting in the middle whenever we produce that chromium hydroxide. So let's see how we would work this one. We know we've got chromium, and it's going to react and form chromium hydroxide. And since we've got chromium already balanced by mass, we've got going from 0 to a +3. Looks like we need 3 electrons on this side. Now there's a real quick fix, it's a shortcut here, but I'm not going to use it because I want us to get used to using the procedure that works 100% of the time. Now in the future, if you'll notice, really all we have to do is just take these 3 hydroxides and add 3 hydroxides on the other side. But I want us to practice, so we're going to do it a little bit differently. Okay? Let's do the same thing we did before. Let's add our waters to both sides. So to get our oxygens balanced, looks like we need 3 waters on this side. So we get our oxygens balanced, but now we've got these extra hydrogens. Now watch it, we've already got 3 here. So we've already got 3 hydrogens. We've got 6 on the left-hand side. Looks like we only need 3 hydrogens on this side. But this is, oh my goodness, drama. We have hydrogens in our basic solution. We cannot have hydrogens in our basic solution. Remember our final step. We need to add hydroxides to both sides that will match those hydrogens. So I need to add 3 hydroxides to this side and 3 hydroxides to this side. I strongly suggest that you do that at the same time or you're going to forget to do it. So what does that do? It turns these into 3 waters. And now we look at both sides and see what we can do. Yes, it looks like we can cancel those waters on both sides. So now you can see why that shortcut would have worked, just adding those 3 hydroxides to the left, but I wanted us to practice that process. So, okay, then the reduction reaction is going to be CrO4 minus, or 2 minus, and it's going to react to form CrOH3 as well. So in this case, we've got a +6 going to a +3. There's 1 chromium on each side, so we're fine with that. But looks like we're going to need 3 electrons on this side as well. So now that we've done that, we can start looking at our other substances that we need to balance. We've got 4 oxygens on the left over here, but only 3 over here. So it looks like we need to add a water over here to balance our oxygens. So we get those oxygens balanced. And now we need to make sure we've got our hydrogens balanced. Look like we've got 3 and 2. Don't forget those 3 hydrogens here. It's a total of 5 hydrogens. So we need to add our 5 hydrogens on this side. But oh my goodness, drama, we've got hydrogens in our basic solution. So our final step in our basic solution is to add that same number of hydroxides to both sides. What's that going to do? It's going to turn this into 5 waters. And our last step for this half reaction is to take this and cancel this water and leave behind 4 waters over here. Now the one benefit in this reaction is that we ended up with 3 electrons on both sides, so we don't have to multiply through by anything. So let's see what we have going on here. Okay, so I'm going to extend the page a little bit so we can get a better look at this. Let's draw, or let's write our final reaction and see if there's anything else that we can cancel out. Looks like we've got 3 OH minuses and a chromium, 4 waters, and our CrO4 2 minus. Our electrons, remember, cancel out in both spots. Now look up here, we've got 2 chromium hydroxides up here, so let's just go ahead and combine those together. There's no sense in writing them separately. We're going to have to put them together in a moment anyway. And then 5 hydroxides. So our final step here is to see if there's anything left that we can cancel out. And it looks like there is. It looks like the hydroxides over here will cancel completely. And it looks like over on this side we'll be left with 2 hydroxides. So our overall reaction, our overall final reaction is that chromium plus 4 waters plus chromium, or excuse me, the chromium and chromate is going to yield 2 chromium hydroxides with some extra hydroxide left over in the end. And that's our final reaction.